So Dan, it's all yours. We don't do a lot of introductions.
Thank you. So I do live here in Texas, and thanks for the invitation, Jan. But in solidarity with Lori and Trish, I went to a meeting in California yesterday and flew in at 1 in the morning, so we could all be suffering from the getting up too early syndrome. Although Satoshi's back in the back somewhere, and he thinks we're all whining, because for him it's Thursday afternoon or something. So for his talk later today, when it's, I don't know, Saturday in Japan. I'm going to talk to you about our new system, which is called FRONTERA. My talk is called Computing for the Endless Frontier, because if you noticed in Lori's slides, Oak Ridge has a machine called Frontier, and while our Frontier proposal was pending, they got that name into the federal budget ahead of us, into like 65 different documents that were way too much work to change. So even though the Endless Frontier was the name of the paper that led to the founding of the NSF, which is our primary funding source, our machine is now named FRONTERA. So close enough. Although I was looking back at the last time I gave a keynote at your meeting, Jan, in 2016, and we hadn't even deployed our previous system, Stampede 2, yet, which is still just, phase 2 of that's only a year into production at this point. So we've got several good years of that left. I do remember at that talk, as I was flipping through, it's the first talk where I whipped out the joke about, saying that the problem with exascale was that it's a number, and everybody knows if you hit it, and you get 996 sustained petaflops, and everybody thinks you failed. And at the time, I thought it was funny to say, what we need to do is move from fixed policy targets to just vague statements about things being bigger and faster, so that we were going to do texascale, was the joke. But so a few things happened. One is the notion of vague policy targets that I was making fun of. That guy won in 2016 in the election, and so texascale is now the name of our new magazine that came out. So that joke has been somewhat institutionalized, which means be careful what you say at this meeting, because it might haunt you for years on Twitter and various other places. So I do primarily want to talk about FRONTERA, which is actually sort of a three-part project. I say 3 parts because for each one, NSF wants to have a different cooperative agreement and a different set of reviews to maximize the amount of time you spend on useful things like report writing and in front of site visit panels. So actually, I think we now have 4 cooperative agreements around this one and 11 overall. So, which means I can have a site visit every 4 weeks. It's fantastic, all year long. So it's just like what we do on Fridays now. So. But it's, anyway, the 3 big phases of the project, and the first, and the one you want to hear about, is to deploy a system in the next couple of months. The storage is actually already up and running, to deal with the largest problems we sort of face across the NSF space now, which gives us sort of 2 distinctions from the DOE systems that the exascale project focuses on. One is we have a much broader code base, right, where Lori was talking about 25 applications that are sort of core for exascale. On Stampede, we've run 4,150 applications at last count. And 2, we're this year, so the codes are all written. And we have no chance to impact codes because we'll be hopefully have users on before the end of May. So first thing, build the system. Second thing, run it and support it and operate it for 5 years, and that's where some of the interesting stuff is that I do want to spend a couple of minutes on. And then the third and perhaps most interesting part of the project is to plan the next system for a 2024 deployment. So it'll follow on after Frontier and El Capitan get deployed, and to think about what makes sense for the second half of the 2020s for, again, the broad science and engineering workflow in a leadership class facility. So, and we have a logo, so it's there. And as Trish just alluded to, we're seeing sort of wide variation in workflows. And this was the beginning of a theme I was talking about in 2016, but it's definitely accelerated, right? So we still have our traditional simulation, still traditional batch, but we're seeing just this explosion of people who want to compute in different ways in the large-scale scientific space. And I have an example in a moment, but web interfaces, Python notebooks, very large interactive analytics type workflows that's really making us change a little bit. What we do, of course, still simulation where we have models, and that's still growing at a ridiculous rate. Machine learning where we don't have models or we're building statistical models and sort of filling in the gap. But most of our problems tend to blend those. So our approach at TAC that sort of led us into FRONTERA and affects at least operations So and I believe, yep, that is Dell about server schedule right now. So on the phone, we've needed to support a broader range of things, and we've built a broader range of systems to do that. In this ecosystem slide, most of you have probably seen before, but we've made more investments not only in interface, which is a huge one, but in a variety of systems. So Stampede 2 is the one that I used to always talk about. Frontera is now the one. You never talk about the one you actually have. So Frontera is the one that's coming soon that now I always talk about, but I just want to emphasize that this is part of the ecosystem we have to put this together. And we really do need a wide range of systems to do that. So this is just a quick snapshot of our production systems today and the different workloads where Stampede is sort of the biggest users. Lone Star is to get out of NSF policy primarily, but mostly our Texas sort of more throughput-oriented users. Hikari is the protected data machine, Wrangler, data-intensive computing, Maverick for interactive and analytics, Jetstream for cloud-type workloads, Stockyard, Ranch, Corral, all different versions of storage depending on the tier and the speed you want, various visualization platforms. And then we have a whole bunch of experimental platforms too, whether it's FPGAs, Chameleon for system software designs, Fabric for sort of alternative architectures, object storage, et cetera, et cetera. So, it sort of takes a village of systems to support the workflows now. And to just point out that these actually are really HPC workloads and not just that sort of other smaller scale computing that we tend not to care about. So this is a pretty big project for us for DARPA. It's called SD2E, Synergistic Discovery and Design. It's basically at this point, although they have started to expand this in other things, the initial focus of this project has been in synthetic biology. And our data flows in it now, they're ramping up, but we're currently getting about 20 terabytes of experimental data in every week. Probably hit 100 terabytes a week before the end of the year of experimental data. In this case, it's a big distributed team with our sort of machines and platform at the center. But we have 6 data acquisition facilities, several of which are robotic, high-throughput phenotyping type things that are actually driven by the results of the analysis on the platform. So, if we don't meet our sort of service contracts on turning around HPC jobs, the robots stop from doing actual data acquisition. There are 15 different modeling teams at 10 universities and 5 companies around the country, and then we're the sort of platform provider. So what platform in this case means is, obviously at 20 terabytes a week, we're soon going to have a multi-petabyte corpus of fairly large data. There's processing for ingest. We run 100,000 assays or so every few weeks on the various experimental, it's flow cytometry and genomics and imagery and mass spectrometry, and all the different experimental facilities have a different component of it. But so there's APIs to do automated upload of that data. All of them kick off workloads that sort of integrate that data into the corpus. You sort of reprocess the data set every time a new experiment comes in. And then these 15 teams that all thought they were going to do machine learning, and sort of are, but it turns out sort of traditional analytics and processing of that data, genomic assembly, resequencing, all that stuff is still the dominant thing they do. But they want to do that from a web platform and share data with each other. There's about 100 modelers in those 15 teams that are working on the data, and they see everything from the web. But it consumes an enormous amount of actual HPC cycles and an enormous amount of high-speed storage. So these are not sort of future or pie-in-the-sky workflows. These are the workflows that we see today, and we've had to sort of adapt our systems approach around this a little bit. So I'll talk about both the traditional and the other thing. I did throw in this slide while Trish is talking. The reason you don't send your slides in advance is they're usually done 6 minutes before the start of the talk. But this is one I gave at Satoshi's meeting at Riken last week in Japan. At the BDEC meeting, Big Data Extreme Computing, there are some architectural things that we change, but we don't necessarily need to throw out everything to do this in terms of our programming models, right? Our core, then those 2 bold bullets are the ones I really wanted to stress. Our core HPC apps should still be programmed like HPC apps, and our core artificial intelligence and deep learning apps should probably also still be programmed like HPC apps. Because eventually they'll figure out there's more than one node in the universe for those things. So with web services to glue these things together, so where we are seeing lots of new programming models and crazy things and APIs, on top of this, the core sort of remains the same. It'd be nice if the security all worked the same way, et cetera. So with that sort of as introduction, let me say a few words about Frontera, and we can slowly pull NDA stuff off of this. Trish said Cascade Lake, so I'm going to say Cascade Lake. I also added the name in there while she was talking. So as we've been on, banned from saying this stuff until the official launch next month, because my standard line is the Intel definition of NDA is stuff that's been on Wikipedia less than 2 years. So RSNDA has only been on Wikipedia like 6 months. So if you've been through that. But so we are building primarily around Intel processors. I'll go into our decision around processors at this point, keeping in mind that the servers are, currently exist. So we needed something that was available roughly now. Dell is doing the integration as we did with Stampede. We'll have, peak performance, as Lori pointed out, is increasingly sort of a meaningless measure, but if you were to measure, it's going to be around 40 on the CPU side, with some additional single precision performance, with some GPUs in one subsystem. Mellanox is providing the interconnect, 200 gig switch-to-switch links, 100 gig to the actual compute nodes. As long as we're in Gen 3, point in going above PCI, going above 100 gigabits. Data Direct is doing the storage. So I think every vendor is sitting in the room somewhere, which makes the talk a little more fraught with peril. As you can see, the goal is to get in trouble an equal amount with each vendor in the things that you say. But we'll have about 50 petabytes of disk, 3 petabytes of flash. We'll talk about how that's organized. And about a 1.5 terabyte per second I/O rate. I mentioned the NVIDIA, and just because of all these things, we have a much bigger front end than we normally had to have the data movers and workflow nodes and support for persistent application services that we just see that we increasingly need. So just to run through a couple of the decisions that we went through, and then I'll do the standard architecture diagram. But most of the system, it has none of the crazy accelerators that we've talked about in the first two talks. One way to define that, if you're writing about it, for Addison's report on this, I saw him somewhere. You might call this boring because it's mostly a CPU-based system. All of the users that we talked to in doing this, I think the word they used for the boring was useful when they said that they could just compile their codes and run. So what we did is went with the highest bin Xeon we could get our hands on, because all of the experience of the last few years, especially when we think about this notion of 4,000 applications, right? In fact, we just selected the early users. There's already 34 teams just for early science. That'll probably expand to 100 teams this year running on the machine. Many of them are fairly far down the GPU path or sort of other restructuring. There's a few teams using Cocos and things like that. But many of them, especially the PDE-based ones, are not there yet. And we need to be doing production science, in 2 months on this machine. And the thing that is still the universal solution is higher clock rate. And there's no really efficient way to do higher clock rates. You just throw lots and lots of power at it. So we're moving to a 205 watt SKU of equivalent to the current 8180 SKU in Skylake. And the rationale for that is, although that is not the most efficient way to get peak flops per watt, we think it's the most efficient way to get delivered watts per flop. Because the very extremely parallel lower clock rate stuff, we just get lower percentage of peak out of it across the big applications. And so even if we have less theoretical efficiency against peak flops, if we have more actual efficiency because the yield, the percentage of peak we get on the average code goes up, it turns out to not be that inefficient, to just throw a whole lot of power at the clock rate problem. So we're going with the very top bins. The other thing, of course, is that all of our users are remote and none of them are involved in our power bill. So from their perspective, power efficiency is 100% our problem. And in fact, even in Stampede 2, what we see is we know that it's a mix of Skylake nodes and Knights Landing nodes. And from an acquisition cost and an operating cost and sort of science delivered per dollar cost, Knights Landing is the clear winner across our workloads. All the users want to run on Skylake because their job goes faster for them on the Skylakes. And the other one is more cost effective. They don't care at all. So Not in the least. We've even changed the charge rates. And, you know, how fast their stuff goes is the only thing that matters. So, so versus Stampede 2, you know, we went with the chip that we think is most widely applicable across the science space, and we've pushed up clock rate, core count, main memory speed, because given that we don't have time to rewrite stuff with a multi-year horizon, this is the closest thing to free performance we could come up with for our users. And in fact, one of the competitors on another proposal who lost to us and said, in the way that competitors give you compliments, that said, he said, "I wish I had the guts to do something as boring as you did." So, I'm going to frame that somewhere, I think. But anyway, there were 60 million reasons my answer was better, though. So, so anyway, that was sort of processor decisions. File system. So most of you have run or interacted with an HPC system. If you were to put the word downtime in your head, the first association that would probably spring into mind is file system, because we know this is the weak part of everything we do is scalable file systems. And the primary reason for that is it's pretty easy to isolate users in terms of compute, because you just give them their own nodes, right? And if they screw up those nodes and run them out of memory, crash them, do whatever they want, they only affect their job. But the file system is maintained throughout all the years is the one shared thing that's still really shared. I mean, to some degree the interconnect, but you can sort of semi-isolate that. And it's harder to sort of crash it in the traditional method. But the file system, one user can do something pathologically stupid. You know, run Hadoop. You know, while one open close seems to be a pretty common pattern. You know, write 4 bytes, open the file, write 4 bytes, close the file is one that we see a lot, and then do that across 100,000 files, and then run 50 copies of that job. You'd think that would be a rare case, so that means like every 3 days something like that happens. But what our experience has been is, one, of course, it's a place we don't have user isolation, so it's the source of almost all downtime. And we hardly ever have a user that stresses all the capabilities, bandwidth, capacity, IOPS, right? Some of them push one of those dimensions, but they very seldom push all of them from a single user, right? Somebody's doing massive RAID I/O, somebody's doing lots of really tiny files and transactions. Somebody has 1 billion files. I'm trying to cut down on those. We have 4 billion files on Scratch at the moment. So, nobody really stresses all those dimensions, and we used to sort of build one big Scratch file system as we thought about the design, because the only way we could get the bandwidth for the high bandwidth users was to aggregate a whole bunch of spindles, right? So we'd build this massive file system for the occasional user that had the high bandwidth need, and we'd sort of screw everybody else in terms of reliability by putting them on that file system. And in the age of solid state storage, we don't have to do that anymore, right? What it's done for us more than anything else is decouple bandwidth and capacity. They're sort of separate variables that you can just buy separately now. So it finally occurred to us, why are we still building one giant Scratch file system and trying to do a one-size-fits-all? So we're actually going to have 4 file systems that are Scratch, 3 of which are traditional disk-based file systems at 100 plus gigabytes a second that we'll just round-robin users onto. So then the while one fork open code will at most take out 1/3 of those users when that file system goes down. But for the ones who we actually see in our analytics that we run, drive, bandwidth, or IOPS, we're going to build an all-flash file system for them. And we're not going to try and do some sort of HSM. We're not going to try and integrate it as a burst buffer. We're not going to do any non-POSIX semantics for it. It's going to be just a 3 petabyte POSIX all-flash Lustre file system. So it'll look like a file system. And you'll just, like Scratch, when we need the space back, get off of it and move to one of the lower tiers of file system. But all manual moving, opt-in, users have to prove to us that they need it, or we're going to leave them on the conventional file system. So by breaking this across these 4 parts, so one, no file system that we're building in this machine is bigger than a file system that we've already built. We already know we can run Lustre at 25 petabytes. We already know we can run it at 2 billion files. We know bad things happen when you go past 2 billion files in terms of concurrent use. So we'll have a set of 20 petabyte file systems, and then this high-speed one for the people who really stress that, which turns out to be like 3% of the users to begin with. So from the perspective of individual users, we expect it to be higher reliability. We'll see. Those are famous last words. I'm going to regret that. But also everything's POSIX. There's no exotic interface from the user perspective. No, well, I wrote to this buffer, and later it will appear in a file system I can LS, but it's not there now, and it may not be coherent. All of that's out. So again, simple, more boring than the next guy sort of design. So, the overall system ends up looking something like this. I'll talk about some of that stuff over the dotted line in just a minute, but we'll have a whole bunch of front-end nodes to deal with the automated services, InfiniBand at the core, and then multiple kinds of storage and multiple kinds of compute to do it. I said our rationale for power and why we can, justify using the very high power stuff. As it turns out, you still have to get the power, so that still costs money. So we're at about 6 megawatts, small in the DOE scale of thing, but Stampede 1 was actually our biggest one up till now at 4.5. We still need to run Stampede 2 next to it, which is only about 3. So we'll be pushing 10 at this point, but there are some things we can do to make up for those high power chips. In terms of infrastructure, first of all, we're just doing direct water cooling of all the primary compute racks because we just can't run these chips past 165 watts in air cooling, and we've tried. So for the 205 watt chips, we're just going to direct water cool every chip in the system. The rack density is 65,000 watts now, for those of you who are building out data centers. For these, for the GPU piece, where we're doing sort of a mix of parts, but particularly for the sort of lower grade cards where temperature matters an awful lot, we're going to do oil immersion cooling for them with GRC, who's also here somewhere. So there'll be some oil immersion. We have about 250 kilowatts of solar going into this now, and we're going to buy about a third of the power for it from West Texas Wind, which makes me feel better about 205 watt parts. The important thing is that I feel better. We have a really big team, 6 minutes to go, supporting this, so I want to just briefly acknowledge all of our partners in this because this is way too big a project for us to do ourselves. A lot of the partners are focused around phase 2, so we have our usual partners of Ohio State and Cornell, and we've added Texas A&M around operations for phase 1. So Ohio State for MVAPIC, of course. Cornell has always done our very successful online training. And then we have a whole bunch of partners, including Rick Stevens at Chicago, but Caltech, UC Davis, Cornell, Georgia Tech, Princeton, Stanford, Utah, around sort of our planning for the phase 2 system. And then most all vendors are on this list. If you're here, you're probably on the list somewhere. And if you're not, we'll probably add something from you at some point. And then we have various partners around UT, including hey, this is probably a good place to announce this. So what used to be called ISIS, turns out that acronym has run into some marketing problems in recent years. The Institute for Computational Engineering and Science, which is now, and many of you work with a number of people from there, in oil and gas in particular, Omar Gattas, Mary Wheeler, are all on that institute. Omar is a co-PI on this project, but it has recently been renamed just 3 weeks ago by the Regents as the Odin Institute for Computational Engineering and Science for Tinsley Odin, who again, many of you know. So now we're just going to call it the Odin Institute, because OISIS is also not a good name. So Odin Institute here on forward. So with my last couple minutes, let me just say some things about support. So back to the science case I made in the beginning, we've had to change the way we run systems some. So, but for purposes of justifying to NSF that we still need a lot of budget to do this, we still have to do all the things that we've always done, right? Support multiple thousands of RPMs, 24/7 operations. They're sort of routine in some sense at this point, but they still cost a lot of money. So these are all the things that you've always expected in traditional. These are two, but slightly newer, and not everybody does these yet. We do, the new MVAPIC, we're auto-tuning for the actual state of the network, so it'll recompile itself periodically. And tune for our MPI implementation. We still do automated performance monitoring. There's a few minutes I could dive into that, but with data mining, we look at every job statistics to drive our consultants to where the problems are and to find the WA1 open fork type people. So, and because we only have a few hundred projects on this machine, we're moving to Slack for user support, so you can just directly talk to us. But those are still sort of all vanilla traditional things. The new stuff's more interesting. So we are doing full containerization support. So we've done it on Stampede, Hikari, and Lone Star, and we're going to do it on this platform and every other platform moving forward. at least Singularity and probably RunC and probably Charlie Cloud. Singularity Slurm integration is complete. We have, from the repositories we pull for Singularity, just in terms of our ability to scale up application support, we have 14,135 containerized apps you can check out and run without us having to do any building and code support. So, given the volume of applications we have to support, having somebody else build the first 14,000 is kind of useful. We are doing protected data support. It just seems to be everywhere. So, given the university space, if you can eventually tie it to data that any human was ever involved in the acquisition of at some point, eventually it's going to have compliance requirements. So we're just ripping off the Band-Aid, and it's going to be everywhere. So patient data, cancer data, any of that stuff is welcome on the system. And again, these persistent VMs that I mentioned to support REST APIs, to support other people's REST APIs for Atlas and CMS and LIGO, IceCube, one of the new ones that we're supporting, they all use various different APIs to glide data in and out and schedule work. So we'll have sort of native workflow. And I mentioned portals are becoming big in all of the various projects, so we're just going to put up a set of default portals in front of the system. And so with 2 minutes to go, just two last things to say about this. One is, as I mentioned, the phase 2 stuff we think is pretty interesting to figure out the next 5 years, and we've never had this sort of long-term commitment from NSF before to do planning, sort of more in the style that DOE actually gets to do. So we'll be standing up a number of testbed systems around FPGAs, around the Optane NVDIMMs that Trish mentioned. We're putting a quantum simulator in with our partner at Stanford. We'll do some things with tensor processors and other things. Apparently, I discovered at Supercomputing, when Intel said this in the keynote, that we were the first Optane deployment in the field, which I didn't know about until then. So, but Optane coming soon. So we'll have about 200 terabytes of it in a smaller set of nodes to mess around with. And of course, we'll be keeping tabs on DOE and everybody else. And then finally, last thing is that we did actually fund Microsoft, Amazon, and Google as commercial cloud providers as an active part of the project. Because after 150 talks, and I think Jan and I together have been to 46 workshops, shall we say, on cloud versus HPC, it is not an either-or decision, right? It is not a binary decision. They don't really do the same thing. So, so money where our mouth is on this. We're going to bring in the cloud, not to do our computation, not even to do burst, although we'll probably play around with burst, but given the amount of data we have, I just don't think it's going to work. But we're going to use the things that the cloud works well on. One is sort of publishing and sustainment of data. If you want to publish a data set that we would have normally sent to tape and put it out there and say, here's my analytics portal on it for all time, we'll be happy to pay to get it out there and then hand you the bill later. For doing that, and then access, as we have these sort of composable workflows of HPC services, there's some things that they have that we don't. So, got it. There's no point in us doing natural language processing, right? Just call Siri to do that stuff, right? So there are some big services we can use, and also they get to deploy a lot more than we do. So if I want to play with the latest FPGAs or tensor processors, might as well do that on the cloud. So they're all funded pieces. So I was going to bring some examples from that. But the ecosystem keeps growing with these new sort of leadership systems in the front. And thanks to all the people who've ever given us any money, because that's just part of the director's job. So, and I'm at minus 17 seconds, so I'll stop there.
I know we're running a little bit late, but if there's one quick question, we can take it. If not, Dan, we'll be hanging around so you can be in a networking call?
Yes.
Okay. So
well, I got to call my program officer for 5 minutes, but after that, yeah, I'll be here all day.
Yeah. So the NSF was listening, by the way, so now there will be a meeting every Friday.
There already is.
Yeah, but now it's actually institutional.
It's not possible for that to be intimidating at this point.
Let me let's thank our speaker again, and always great to have you. And there will be more updates.
Yep.
So.